Hi, I'm Bob Doyle, the information philosopher, webcasting from my ITV studio in Cambridge, Massachusetts. I'm hoping to reach philosophers and scientists around the world to help solve some great problems in philosophy, in physics, in biology, and in psychology. I also hope to reach any of you wondering about the deepest nature of reality and our place in the universe. We live in the information age, but I find that few philosophers or scientists understand the nature of information. Information is neither matter nor energy. Information needs matter to be embodied in our brains, for example, and it needs energy to be communicated over the internet, like this lecture coming to you electronically. But matter and energy are conserved quantities. It may be hard to believe, but the total amount of matter and energy in the universe today is just the same as there was at the beginning of the universe, nearly 14 billion years ago. And if the stuff of the material world is just a fixed total amount, what can possibly explain all the evolutionary change that we see? I'll explain those changes as the information and order in the universe, which has been increasing since the beginning of time, despite the second law of thermodynamics and the increasing entropy, which destroys order. Change, for me, is simply the arrangement of the molecules and atoms into what I call information structures, like the galaxies, the stars, and the planets. But stars are passive objects under the complete control of physical forces like gravity. However, living things, you and I, are dynamic and growing structures under our own control. I'll show that we are forms through which matter and energy continuously flow. And I'll show its information processing from the DNA in our cells to the thoughts in our minds that controls those flows of matter and energy. Information is the modern spirit, the ghost in the machine, the mind in the body. It's our souls, and when we die, it's our information that perishes. Only our matter remains. So let me tell you that you can reach me, Bob Doyle, at informationphilosopher.com if you'd like to correspond. And that today is the end of our second week of lecturing this way online. And will be, as usual, the topic today is Albert Einstein. And Einstein is the subject of my next book, which let's spin out just a little bit larger to see what we have here. In this book, I'm hoping to show, with a careful study of all of Einstein's papers through the years, from his first really critical important piece in 1905, the year in which he produced his great article on special relativity, another article on the molecular nature of matter and the Brownian motion, but finally a paper which is often called a paper on the photoelectric effect, but it actually contains Einstein's idea that particles, light consists of particles. Let me just back up here to this screen and see that we have Albert Einstein's page on the Information Philosopher website, which you can find by going to our drop-down menu, the long navigation on the left-hand side here. I can, I think, go back out to this to show you full screen. And that navigation on the left-hand side with lots and lots of links consists of many philosophers, but also scientists. So the way I've located my work on Einstein is to scroll down through all of the work on philosophers, some 200 of them that I've studied over the last several decades, and written critically about their work so as to give you resources on the web should you want to become an information philosopher in the future. So to get to past all the philosophers and into the scientists, we scroll down. Eventually we'll come to Einstein, and let's just click on Einstein. And now we can shrink it back up a little bit the way we had it at the start. And what we see is some text, my analysis of Einstein. And as we go down through the page past the introductory material, we come to individual important articles, of which the first is this one called the light quantum hypothesis. So what I want to do is tell you a little bit about where I get my material on Einstein for something like this book. Basically, I've been for years reading the collected papers of Albert Einstein, which is was for many years my main source, besides all the books about Einstein, biographies and so forth, and all the books that included his articles. But not all of Einstein's work was available when I first began studying him. And when these books came out, the collected papers, this is volume 2 of about 17 volumes out at the moment, it was an enormous resource for research on Einstein. And what I am happy to say is that today, all of the Einstein papers have been put online. Let me just go here. This has given us an enormous resource, all of which I have had in print form for some years, but now I'm able to put them up in digital form online. And here we're at a website that's maintained by Princeton. The link is einsteinpapers.press.princeton.com. And here we see the first few volumes. This is volume 1, available in both German and English. And here's the second volume 2, available in German and English. And this is the English copy that I have here on my desk. So what I'd like to show you is that if we went to the opening page of the German version, this is a little hard to read, more than a little hard to read, but we get down to paper number 14, and it's called On a Heuristic Point of View Concerning the Production and the Transformation of Light. This is Einstein's famous paper, often mistaken as the paper called Photoelectric Effect. Here it is in German, and we're not going to be able to read that, most of you, but it is important to me to read Einstein in German from time to time and notice the particular use of words that he has for some of his concepts. The most important one is the word he uses for chance, because within 10 years he's going to have to introduce the possibility that quantum physics contains chance. So here's another link to the English version, and let me click there for a moment. And this article is therefore online, available to you, and stop that, which is extremely important. You now have access to, at the moment, 17 or 18 volumes, more to come the next few years. We have Einstein's papers now up through about the mid-1920s. And this becomes a very interesting time for me, and I'm looking forward to the completion of these enormous efforts by Princeton, by Caltech, by the Hebrew University in Jerusalem, all of which Hebrew University owns the papers, and they're slowly being digitized, and they're being translated, and they're being made available to scholars like me, and I want to point them out. They're available to you. Now, whereas online you see the complete works. Let me take that picture right there and put it up on the screen. I think I need to go to the A tab. So here you see his paper in English, and we can scroll this paper up and read his first few paragraphs. And these are his very first lines. And these few paragraphs are amazingly insightful about the digital quantized nature of energy, of radiation. This is an incredibly radical idea. Only 20 years earlier, Ludwig Boltzmann was trying to convince the scientist of his time, physicist, that matter came in discrete objects, which had been recognized by chemists since the beginning of the 19th century. Chemists like Dalton, who had found combinations of atoms into molecules, suggested that there were atoms, that atoms were pieces of matter that came in discrete quantities. Always exactly the same size, which is quite an amazing discovery, that the elements of the universe come made up of elementary particles. In those days it was thought to be atoms, then later came to be thought as electrons around nuclei. And today the nuclei are known to be made up of even smaller elementary particles like quarks. And this idea applied to light was incredibly controversial. And it's this paper that we have on screen here that Einstein is telling his colleagues that he has evidence for the fact that light travels around in little bundles, which he called Lichtquanta in German and light quanta in English. And the idea that light might be in quantital amounts was first suggested strictly as a mathematical heuristic way of doing some calculations by Max Planck. Just 5 years before this paper of Einstein's, Planck had a paper in 1900 that was able to establish a formula, the expression for the amount of light at different colors or different wavelengths, by assuming that there were particles, radiating particles, and that these particles somehow had a quantal property. But it turns out Max Planck really never did believe in this notion of quantum mechanics, as it would become called 28 years later. Instead, he was just doing something that enabled him to get the math to come out right, to have a formula, the Planck radiation formula. But Einstein in 1905, we're going to read through the next few paragraphs here and try to get you a sense of what he could see already in 1905. He's still a relatively young man. So let's go. I want to show you that this paper, which is online for you, I have put online years ago for you, but I don't have to do it anymore, but I'd like to show you the technique that I used. I actually bought the volumes of the collected papers. I have all the existing volumes, and I would actually tear out of the book, in this case, my early copies of this volume are hopelessly marked up with my notes and my scratches of here and here, wondering what Einstein is telling me. And I wanted to produce a nice PDF, a nice clean PDF copy. And I also wanted to scan it for use in my own pages on Einstein. And so let me see if I can find that page. And set this book aside and go to Einstein's page. Maybe I'll just go to this screen where I've got the light quantum hypothesis section of his paper. And you'll see that it corresponds to the same words here. See if we just see, so you see the way I work. Let's zoom in a little more closely, right to the top. And we have the title of his paper, and there exists a profound formal difference. Okay, so we'll come over here to my section on the light quantum hypothesis. And what I've done here is have the Einstein words, plus on the right-hand side, in my little right-hand call-out boxes. Let me switch to another view for just a moment so I can move my mouse around. Here we're coming down my comments in the history of Einstein. We'll go back over some of these later as I try over several weeks of lectures to give you a good feeling for Einstein. But each particular paper will be treated like this one. And I just wanted to start in and talk to you about the lines and what really is it that Einstein is telling us. So his first sentence is, a profound formal distinction exists between the theoretical concepts which physicists have formed regarding gases and other ponderable bodies. These are material bodies. And the Maxwellian theory of electromagnetic processes in so-called empty space. Now, while we consider the state of a body to be completely determined by the positions and the velocities of a very large yet finite number of atoms and electrons, we make use of continuous spatial functions to describe the electromagnetic state of a given volume. Let me just stop there for a moment and say, when we look at a body, when we talk about understanding a material object, we imagine it to be made up of a very large, not infinite, because infinity raises a very interesting mathematical and metaphysical question. Is matter continuous, or is it somehow discrete? And what Einstein is saying here is, we imagine the state of a body to be completely determined. So let me go back to his words here. Completely determined. Okay, and mind you, this is a man who will fight for many years to argue that everything in the universe is determined. This famous God does not play dice. Completely determined by the positions and the velocities of a very large yet finite number of atoms. Here is the echo of the great Laplace and his intelligent demon. You remember that Laplace argued that if we just had the positions and the velocities and could know them, some intelligence, not a human, could know this enormous, not infinite, but enormous amount of information about a very, very large finite number of atoms, then given the laws of physics, the completely deterministic laws of physics, you see in Einstein's sentence, that they would be able, this intelligence would be able to know the entire future of such individual atoms, because the laws of physics, which are completely deterministic, could be used to calculate exactly where all the particles would be at every time, not only in the future, but of course back to the past. And so it would be as if the material universe was such that it could be known for all times, and corresponding to a kind of religious view that there might exist an omniscient being, that in that being's mind all times are equally apparent to the mind's eye of this omniscient mind. So this was a picture that was comfortable for large numbers of people, and especially the physicists of the day. But apart from this vision of material, Einstein is about to tell us a little about electromagnetic energy, which is we think of today as light. We think of it as photons, which is seriously anachronistic, because the name photon won't be used to describe the particles of the light that come into our eyes and so forth, until 20 years after this initial paper by Einstein, in which he says, I think I can tell you that light comes in quanta, in lumps, just like atoms and electrons and so forth. So let's go back to Einstein and look at the line comparing how we think in those days about light energy, okay, electromagnetic. He says, we make use of continuous spatial functions to describe the electromagnetic state of a given volume, and a finite number of parameters cannot be regarded as sufficient for the complete determination of such a state. What is Einstein telling us here? He's saying matter seems to be describable by discrete, finite numbers of things, whereas electromagnetic energy is thought to be continuous. So matter is discrete. Lots of individual objects, when they combine in a large number of them, they look pretty continuous. They look like a big object, a single object, but down deep they're made of atoms. On the other hand, he says, where matter is discrete, quanta, light looks like a continuous quantity, and we need infinite amount of information along that continuum. A continuum, remember, in mathematics is thought not to consist of like the real numbers, 1, then 2, then 3, then 4. Instead, the continuum is thought to have values at every point on the line between 0 and 2, 0 and 1. An infinite number, a continuous number of numbers. You have to introduce irrational numbers, you have to do a lot of things, but Einstein is saying that our work in energy and light is done with continuous parameters. So, according to the Maxwell theory of electromagnetism, energy is to be considered as a continuous spatial function, okay? And that's all electromagnetic phenomena like electric fields and so forth, including light. Well, he's just reiterating what he said earlier. So light energy is continuous, while the energy of a ponderable object should, according to the present conception of physicists, be represented as a sum carried over the atoms and the electrons. This is an amazingly powerful claim by Einstein, that there's something different between matter and energy. And this is the Einstein who's about to say, really very quickly, a year later, that although there's a fundamental symmetry between matter and radiation, he also sees that and that will be known as his conversion equation, that energy can be converted into mass times the square of the velocity of light. So perhaps should I say he also sees an asymmetry between the two in the way that we describe them. And so he says in his next paragraph, the energy of a ponderable body, a material body, cannot be subdivided into arbitrarily many or arbitrarily small parts. That's the whole atomic principle. Matter is made up of lumps which are discrete, one after the other. They can't be subdivided. You can't cut an atom, although today we split atoms and split their nuclei and get out nuclear energy. Still, our picture goes down to the nuclei being made up of smaller parts, the protons and neutrons, and even smaller parts, the quarks and various connecting particles like mesons and others that bind the nuclear material together. But nevertheless, what Einstein is seeing, and seeing clearly, is that a material ponderable body cannot be subdivided. Whereas the energy of a beam of light, okay, the energy of a beam of light, and I'm finding it hard to scroll through here, coming away from a point source, think of that as a light beam going out, flashlight shining in a small number of directions, but continuously. According to the Maxwell theory of light, or more generally, according to any wave theory, is continuously spread over an ever-increasing volume. And two things here. First, Einstein is telling us that the theory of light is a wave theory. It turns out it used to be, 2 centuries earlier with Newton, a theory that maybe light came in particles. Newton's thinking for that, we can take a breath sometime and realize that was a foresight that turns out to be true once Einstein works on light. But wave theory and continuous theory is the characteristic of light, electromagnetic radiation, when Einstein writes. So I asked this question alongside to think about what it is he's telling us. How can energy spread continuously, okay? I mean, a light bulb in the middle of a room or a candle flame goes out in all directions and it fills the space. And there's no sign in a continuous wave theory that there is any break in places where there is no light. The light seems to fill the volume. But how can energy spread continuously over a large volume and then later be absorbed in its entirety, which is what we're going to see, without contradicting Einstein's principle of relativity? Einstein is starting to see this discrete nature as a problem when you try to reconcile the discrete nature of energy and light with the principle of relativity. And we'll have to develop our own description, but the fundamental idea of what Einstein saw in 1905 is here in his few paragraphs. So let's stay with him for a while. The wave theory of light, which operates with continuous spatial function, has worked well in the representation of purely optical phenomena, and it will probably never be replaced by another theory. It should be kept in mind, however, that optical observations refer to time averages rather than instantaneous values. And here Einstein is already seeing that maybe if light is, in fact, as he's going to hypothesize, made up of particles, that most of the time there are so many particles, so many quanta of light, that it appears to be a continuum. Appears to be a continuum, and actually is just like the atoms that make up a solid body like ourselves, the wall behind me. It looks to be continuous, but we know ponderable, as he calls it, matter, it consists of discrete particles of matter. And now Einstein is saying maybe that's the case for light. In spite of the complete experimental confirmation of the theory as applied to the diffraction of light, the reflection of light, light that gets dispersed when it goes through various media, it is still conceivable, says Einstein, that the theory of light, which operates with continuous spatial functions, may lead to contradictions with experience when it's applied to the phenomena of emission and transformation of light. And that's in the title of his paper. He's talking about producing light and transforming light into captured by material particles and emitted by material particles. This is called the emission and absorption of light, and then the transformation of light when it seems to become just part of the energy of an atom as we now think of it. It seems to me, says Einstein, that the observations associated with black body radiation, and that's the work of Max Planck that we just described, and there the observations tell us how much light is in the infrared, how much is in the red, and then the orange and the yellow and the green and the over to the blue and ultraviolet. That distribution of light needed a hypothesis by Max Planck that he could use discrete quantities, and that enabled him to get to the black body law. But he did not assume there was anything really discrete and particulate about light. Max Planck did not assume what Einstein is telling us seems to be the case in this paper back in 1900. And then ideas like fluorescence. Now, some of you may know we have fluorescent lights today, and that's a process by which atoms are stimulated into higher energies and then cascade back down and give off this and light. The production of cathode rays. Now it's interesting, when I was younger, cathode rays were flying around inside cathode ray tubes, CRTs we called them. We're now living in the age when television no longer consists of glass tubes, like great big glass bulbs, inside which cathode rays, otherwise known as electrons, were being fired by dropping through a potential between two metal grids and were sent toward the front of the screen where they would light up the screen, scanning across and giving us our television pictures. Today, that's ancient history. We're now doing all of our television with flat screens with LEDs behind them, or even today, individual LEDs or light-generating elements making up the surface of the screen. So there'll become a time when people won't remember much about the early days. And he mentions Einstein saying, consider these observations, finally ultraviolet light, when it falls on certain metals, you shine a light on the metal and off comes an electron. This is the part of the paper which is known as the photoelectric effect. And it's the idea is that light falls on matter, and inside that matter there are particles, atoms, which can eject an electron because the energy coming in is greater than the energy binding the electron to the atom in the metal, and out comes an electron. So he says, all of these things are more readily understood if one assumes that the energy of light is discontinuously distributed in space. And this is the radical idea, of course. So we have just a few more paragraphs here. In accordance with the assumption to be considered here, the energy of a light ray spreading out from a point source, remember our flashlight, light is going off in some direction, or a light bulb, Einstein says, he is not, we're going to assume it is not continuously distributed over an increasing space, but consists of a finite number of energy quanta, which are localized at points in space, which move without dividing, just like atoms or electrons, and which can only be produced and absorbed as complete units. Now, I note on the side, the explanation for what Einstein is describing here was actually doubted until the discovery of the Compton Effect in 1923. So what Einstein is telling us now in 1905, it will be 18 long years, really long years. They travel up to Niels Bohr describing a model for the atom with electron shells up and down and interactions by which light is given off when the electron changes its state inside the atom and so forth. It takes us up to World War I, 4 years of horrible war in Europe, and terrible depression conditions in the 1920s. And fortunately, Compton is an American doing his work in the US, and he will finally confirm this photoelectric effect that Einstein is describing here, and see that units are coming off. But he still was skeptical. Others saw that the experiment Compton did confirm Einstein's work. And here he says, we therefore arrive at the conclusion, the greater the energy density and the wavelength of a radiation, the more useful do the theoretical principles we have employed turn out to be. For small wavelengths and small radiation densities, however, these principles fail us completely. And what Einstein is saying here, somewhat subtle, is that long wavelength light, like red and infrared, and we have radiation today that goes into what's called microwaves, longer and longer and longer waves, radio waves, and so forth. Those seem adequately describable by a continuous wave theory. But when you get to higher and higher energies, shorter and shorter wavelengths, ultraviolet wavelengths get smaller and turn into X-rays and gamma rays and more energetic. Particles of light is the way we think about it today. There's something wrong with our theory, says Einstein. And it will take him a few years before he can show us exactly what the problem was and what the solution looks like. But he concludes, and this is just the part I've abstracted from the paper that we showed you, he concludes that monochromatic radiation of low density within the range of validity of radiation formula, not by Planck, but by Willy Wien, who is a good friend of Planck and Einstein. It behaves thermodynamically, and that's a subject we'll try to get into, statistical mechanics and Boltzmann's ideas about thermodynamics and entropy and so forth. But for now, Einstein's conclusion is that electromagnetic radiation behaves thermodynamically as if it consisted of a number of independent energy quanta, that all of these little elements of light are completely independent of one another. They're traveling around much like gas particles, but it turns out they mostly travel in straight lines, as we see that light does. They don't interact with one another, so there are some important differences here. But this is his work. This is Einstein's work to say that that light cannot be spreading out continuously in all directions. If the energy is absorbed into metal as a complete unit, it's instead of being a continuous and therefore dividable into smaller amounts energy, it must be a lump that can only absorb as a unit. And then it ejects another unit, a photoelectron, in the photoelectric effect. Okay, well, that's what I've been hoping to give you a really deep dive into this very first work of Einstein that became the foundation for 20 years later by others, notably people like Werner Heisenberg and Niels Bohr and Paul Dirac and Pascual Jordan, Max Born, those who are thought of in the late 20s as the founders of quantum mechanics. But what those founders did, and deservedly great reputation, a great contribution, what they did is allow us to make calculations, exact calculations of what's going on in quantum phenomena. And quantum physics today is the most accurate theory of the world. And the number of significant decimal places of the calculations is somewhere up in the 15 significant digits, more accurate than anything that we can measure easily, because measuring apparatus, normally we're happy if we get within a few percent when we weigh things, but in quantum physics we are down to doing measurements that are much, much more accurate, and the more accurate we get, the more we agree with the mathematics, the computational capabilities of quantum mechanics, which is what the founders really did. But they had no conceptual improvement, I will try to show, no new concepts. Indeed, what they wanted to do was bury some of the strange behaviors, mysteries we're going to call them, of quantum mechanics, by saying, don't look there. Don't try to understand what's going on there, because it reveals some mysteries that are not possible in classical physics. Quantum physics genuinely contains mysteries. When Richard Feynman says nobody understands quantum mechanics, he's talking about something very serious, and we will be going into them. Okay, for today's lecture then we'll stop here. And I would like to just tell you a little bit more about the work that's going on with my website and my materials that are available to you. Let's just scroll back up to the top here on the Einstein page. And notice that I've added 3 little icons here. Let me just see, I better expand that a lot. Let's see if I can do that. Okay, here we go. That's pretty good. I am going to try to add social media capabilities to my website. My website is almost 20 years old, and it's always been a knowledge base like a Wikipedia, and it's grown to have a huge number of areas like my problems, about 16 or so of those, my knowledge drop-down, my explorations of the problem of value, is there objective value in the universe, free will, etc. So I've got lots and lots of pages, and lots of pages on philosophers. Let's take this to full screen for a moment. And it's these 3 new icons, which younger ones among you know all about. One is a link to a Facebook page, which I've started, that is mostly going to carry the videos that I'm producing, like this one today. And similarly, YouTube, this is the YouTube icon. This takes you to my YouTube page. Let's just click it and see what happens. Nothing happens. Oh, there we go. So I need to create some artwork here for the header, but here's a link to my yesterday's lecture on metaphysics, whether or not we can support the idea that there are real possibilities in the universe, and so forth. So let's go back if I can. I guess I have to do this. And here we are back. The middle little bird, of course, is a Twitter linked to my Twitter account. I hope to actually improve this and make it into a tweet link that when you click on it, it will get the page you're on, of the thousands of pages in Information Philosopher. It will, I hope, I'm hoping to write the code myself to identify the page you are on, and then go to your go to a tweet page that lets you tweet the title of the page and so forth, and maybe some other things. I have a lot of learning to do to make this happen, but let's see what happens when I click on this one. For now, it goes to my Info Philosopher Twitter account. Let's see if I can increase the size of this one a little bit. So you see it has @InfoPhilosopher. It also links to, it links here to my informationphilosopher.com. So it's not clear where, I guess up here in the address bar, it's twitter.com/InfoPhilosopher. Neither YouTube nor Twitter would give me Information Philosopher as a handle or a username. It was too long, so I picked this Info Philosopher, and I use it on not only Twitter and YouTube, but also on Facebook. And here are tweets I've been giving lately. Now, I've just started doing this tweeting, except for one I did a few years ago when I first set up this account, which links to an article in Harvard Magazine, which I hope you might look at sometime, on my new model of free will, which is described here as a two-stage. There are 2 steps was the title of the Harvard Magazine article, and how I trace this to the work of William James. Okay, so let's go back to my original page, and finally there's a link to Facebook. I won't go there. It doesn't really go quite to the right place that I would like it to go, and I'm still working on that. Now, did I want to tell you something else? I guess one thing that's here, which those of you who have been looking at my work for a while may notice, is that I've eliminated a couple of things on this line, this level with the search bar. At any time you can enter any word into the search bar and find all the occurrences of that concept throughout the Information Philosopher website. It's really a wonderful way to get a handle on the different articles I have, because it goes to problems and the different people who might have thought about that problem. I use this myself all the time to try to drive around, and in future lectures I will use it to drive to pages and then go in and talk to you, try to teach you some of the knowledge that we put on those pages. Over here is my current translation using Google Translate that can translate the website for you into French and Italian, German, and so forth. I hope you will find that useful to give you a gist of the page. This is not translation the way it should be done, with all the idiomatic expressions done correctly. Instead, it gives you a gist. If you don't quite know what my English is saying, you can definitely look at it in your language. I hope to add a few more languages over there very soon, and Google is talking about giving us translation quickly, rapid translation in 40 languages, which I also hope to incorporate at some future time. Finally, among the bars up here, I've now added one on particular problems. Let's see, no, that's knowledge. Particular problems. And what I'm hoping to do with these problems is to create a YouTube video a short one, maybe somewhere between a 5-minute and the type of 15-minute TED Talk video on these major problems, which it may sound like hubris, but that an individual, one person like me, can actually have plausible or suggested solutions to so many problems. I mean, most academics would be happy to have just done something a little original in one of these, but I do think the new methodology using information rather than language, rather than arguing verbally with one another about the problem of identity, for example, which is a deep metaphysical problem, the problem of measurement in quantum physics. All these problems, by thinking about them in terms of the underlying information, I hope to be able to give you a stronger insight into what they are, and I reach out to other philosophers and scientists to try to do the same thing and criticize the work I'm doing. So that's our lecture for today. Let me remind you, you can reach me, Bob Doyle, at informationphilosopher.com if you'd like to talk about or interact with me on some of these subjects. I'm going to drive over here and I'll just try to find a little page like this one. It'll give me a little music bed as we go out of this end of the second week of my lectures online, hoping to reach people around the world, from philosophers and scientists who are really the most expert in this area, far more expert or at least experienced than I am, but also reach those of you who really would just like to know a lot more about some of the things you read about, especially those things that seem to be quite mysterious and strange, like the entanglement of particles that can then signal one another at faster than light, and this problem which Einstein introduced to us today, that there are some ways light looks like waves, but other ways it looks like particles. So, looking forward to seeing you again next week. This is Bob Doyle, the information philosopher in Cambridge, Massachusetts. Thank you.